when you bend it this way, the IV, this guy and this guy takes up most of the load. The middle one is not doing anything. And so that's why when they make carbon fiber structures, for example, they only care about the top and the bottom. So if you want to make a carbon fiber plate, for example, like this thing, what you're going to do is you're going to put a skin of carbon fiber on the top, a skin of carbon fiber on the bottom, and in the middle it can even be a styrofoam, and it'll be very tough because the top layer and the bottom layer is what is important. So this is the strength of sheet metal structures. Okay, this is sheet metal, right? In fact it's very, very thin. Chinese made, of course. It's very thin. I mean, if you squeeze it, I mean, look, it's starting to deform already, right? These are very thin sheet metal, but why is it strong in sustaining this weight? I mean, relatively strong compared to the thinness of it. Because they put it into enclosures, okay? So what these are all bent into tubes and shapes that are closed. If you notice, none of these are open curves, okay? So everything, so these sheets are bent around and then they welded, right? So lots of spot welding throughout. And that makes the sheet become stiff. And so the entire car body is basically almost like an origami. It's basically sheets bent over, seam, spot welds, everything. So you end up with something very lightweight and very stiff at the same time. So that's what the unibody is like. And again, we'll talk more about chassis. No, we don't have a topic on chassis. But this closed structure is what's giving it the stiffness. And this is why convertible cars have the problems. If you notice convertible cars, it's, of course I'm drawing a box, but it's open, right? See, the fact that this is open creates an open curve. So if I cut this chassis, it's not a closed curve. It's like that. And so with convertibles, what often happens, if you take hard turns, this thing, the gap, you'll see the gap doing this. So if you take hard turns, the chassis actually twists. And because it's not enclosed like a typical sedan, you actually have shifting of panels. And so if you not careful, you can get pinched if you put your hand here doing the turn. So again, car chassis, they make everything closed curve, gives you the stiffness. Also, the front side is also responsible for absorbing collisions, right? And sheet metal, they have these crumple zones. If you notice accidents, if you see an accident and the front is like totally crumpled, it's a good thing. Most likely this guy survived because that means the energy is absorbed, right? What happens in a collision? You need to remove kinetic energy. And this kinetic energy is absorbed in the crumple zone. So when I was in the United States, before I went back, my professor and I, our research is on lightweight structures. And the way they try to save weight on these structures is they pick non-critical parts like this part, the roof, part of the roof, not the pillars, but the roof. maybe the tray in the behind where the speakers are usually, they make that out of cheap material and lightweight. And so you have multiple material go into the car chassis to make the car lighter. And why do they try to make it lighter? Well, before hybrid and EVs, the only way to improve the fuel efficiency is weight. Do you know why? Why is reducing the weight have a significant impact on efficiency?
Because more mass, definitely more force. More force requires more fuel.
Okay, but that is not an issue in highway driving. It's only an issue in city driving. Why?
Because in cities, you start from standstill, so it requires more first gear, like higher ratio. So first gear usually takes more power from the engine, but cruising you more use more momentum to go forward rather than standstill.
You're getting somewhere. So what is the source of fuel inefficiency? Where are fuels wasted? When are fuels wasted?
When you start.
Not when you start. When you start, you burn fuel, you get kinetic energy, right? You get kinetic energy. So you're not wasting fuel. You're using fuel. But when does fuel go into waste? When does energy goes into waste?
Braking.
What happens during braking?
You slow down the kinetic energy.
So the kinetic energy goes into what kind of energy?
Heat.
Heat in the brakes.
Oh yeah.
And what can you do with heat? Nothing. It just goes away into air, right? And so it's like me using my, using my money, I buy my fuel. My fuel goes into kinetic energy, which is still useful for me. And then when it goes into heat, I lost my money, right? In highway driving, where is energy wasted? Where is it gone to? In city driving during braking, and it goes into brake heat goes into air, and you cannot capture it.
Drag.
Friction, yes. The rolling friction. What else? Aerodynamic, air drag. Air drag becomes heat, heat goes away. Actually, if you think about from a global perspective, any inefficiency in mechanical or energy conversion goes into heat, right? The fuel, you combust the fuel to get motion, but do you know the average efficiency of a gasoline car?
25.
Used to be 25, it's getting better with Atkinson and all that, it's about 35 now. But it's still very low, right? Electric motors are 98% efficient in converting electricity into motion. But this inefficiency in gasoline cars are inevitable, right? Because of the nature of combustion. So 35% goes into motion. Where the rest go? What about 65%? What does it become? What kind of energy? From fuel to motion, converting from fuel to kinetic energy. 35% goes into kinetic energy, and 65 becomes heat. Again, heat is always the culprit, right? And so your engine becomes hot. And what do you do with that heat? Nothing. We just give it away in the radiator and the cooling system, right? We cannot use it. I mean, we wish we can use it to heat up our water, but that's at home, not in the car. So you cannot avoid that inefficiency. And so coming back to the chassis, because in city driving, most of the inefficiency is in the form of accelerating and braking. The lighter you make this, the less waste you end up burning in braking, right? So that's the inside. Many of you know the engine, right? We talked about the efficiency of the engine a little bit. It's about 35, maybe 40 in a very, very efficient engine. But you know, cars. When you sell cars, what do you sell? Other than the looks and the comfort,
Fuel economy.
fuel economy. But there are also people like us who like performance. And so this is the trade-off, right? This is a trade-off in any engineering. If you think about engineering, it's all about trade-off. You know, you design this table, of course you want to make it strong, but also you want to make it aesthetic. You also want to make it cheap. So as an engineer, when you design something, design is always about trade-off. And we have to pick which one we want to optimize. So the engine, in the same way, you have to optimize for fuel efficiency, but you also have to optimize for performance. So what are some tricks that people do to get both in designing an engine? What kind of technology they come up with?
VT, VTEC.
VTEC. So you're efficient in the lower RPM range when my wife or any old lady driving it, right? But when we drive it, we rev it up and we get what we want. So you get these two range. Turbo actually is also a way to get efficiency below the turbo rev line, and you get power after that. Transmission. Oh, let's talk about the sensors. So what are the control systems or the mechatronic aspect of an engine? The ECU controls based on what kind of sensors? I mean, I know it's a lot. Just mention some of it. Mass airflow? Mm-hmm. Or map, right? One of them. Crankshaft position, camshaft position for timing.
Oxygen sensor.
Oxygen is a big one, right? O2 sensor, or they call it lambda sensor.
Fuel pressure sensor.
Fuel pressure. And what does it control based on this? Well, the big one is actually the air, right? And the O2 sensor. They kind of the main input variable. They control probably 80% of the fuel injection amount. And then there's some correction, like the coolant temperature. The engine is still cold, they make it a little bit rich, just a little bit. So there are all these multiplier after the main determination, right? So based on the math, and the map will change based on your pedal, right? And then the O2 measures the combustion products at the exhaust. And so it's a closed loop feedback. And so based on that and the RPM, you determine the fuel injection, right? Usually what it determines is the opening. So fuel injection is always under pressure, and then you adjust the opening, right? You open for like 10 milliseconds or 30 milliseconds. Of course, this happens real fast, so in the end, you basically have a flutter. Right? So the amount of fuel is how long do you open the valve. But it's also corrected with other things like coolant temperature. Let's see, what else would adjust that? Well, yeah, fuel injection and timing. But I'm talking about the micro tuning of the fuel injection. I think it's mainly engine temperature. Oh, it also do something else when your AC compressor is on. So your air conditioning. Your air conditioning is a good 1 to 2 horsepower consumption actually. And so if it turns on, they also dump a little bit extra fuel on the fuel injectors. So fuel injection and timing are the two things they control in the engine. Of course, there are feedback, solenoids, and all that. Okay, let's move on. Transmission. So it usually have, especially on automatics, as a separate brain, the transmission control unit. So what would be the sensors going in, and what would be the actuators it controls? The input. What are the inputs? Okay. The vehicle speed, RPM, of course.
Oil pressure.
Oil pressure, the transmission oil, right? How does it decide when to shift?
Load.
Load, right? So you also need the math going in here too. Mass airflow sensor. And then it controls
Or the gear.
how does it control the gear?
Changing oil pressure actuators.
So there are these actuators, basically valves, right? So you have all these lines, right? So the pressure goes into the valves. Valve number 1, valve number 2, valve number 3, and you open and close in logical sequence, like when valve 1 is open and valve 2 is open, you go into the second gear. When valve 1 is open, valve 3 is open, you go into the, so and so. So there is this hydraulic logics. So what it controls are the solenoid valves. There are a few of them, right? And the torque converter, the conversion from the crankshaft, the mechanical coupling, is also not that controlled unless you want to lock up the clutch. It's called the lock-up clutch. In automatics, you have torque converters, and then during highway speeds, you lock it up so there is no slipping. We'll talk more about this in the coming weeks. So automatics has this lock-up clutch. With dual clutch transmission and all that, you got all kinds of other actuators going on. But the PCU itself is usually separate these days because it's getting more and more complex each year. All right, now suspensions. What are the sensors affiliated with, like smart suspensions?
Ride height sensor. Ride height.
Ride height, okay. There is this sensors that measures how much displacement, okay, and it's gonna adjust the shock absorber. It's called adaptive shock absorbers. So again, the suspension control unit. I mean, this is built into the ECU, but I'm drawing it separate for representation. So you have displacement sensors, like how much the road actually put displacement into your suspension. What else? Well, that's the setting. It's also an input to your suspension control unit, right? You can set for adaptive tuning soft or hard, sports or comfort, right? And then what does it adjust? There is usually the damper with adaptive shocks will have a valve, actually. A damper or a shock absorber is basically a syringe, right? It's like the syringe you use for injection. So there is oil here, there is oil here, and there is a tiny valve, but this adaptive tuning sometimes have an extra line going to the top chamber. So when it gets pressed, the oil can bypass this to reduce the damping if you want to. So this valve, or usually driven by motor, is what you adjust, right? The adaptive valve on these shock absorbers. I think that's mainly what they adjust. I'm not aware of other controls in the suspensions. Now, if we take a zoom out a little bit, what is the function of a suspension? Stability by what? What do you mean by stability?
Oh, it depends what your target is.
Mhm.
Let's say off-roading, it's more toward keeping all wheels
Right.
to the ground.
Yes.
But if you're racing on like road and you're cornering, you try to keep
Weight distribution.
weight distribution.
Mhm.
So
The amount of contact force in each wheels.
Yes.
So that part that you just mentioned is often ignored by common people. Most people think suspension is only for comfort, right? But the biggest job of a suspension is actually to keep all four wheels on the ground, touching the ground. So it's a traction concern. Imagine if you don't have suspension, your car will be flying all over, especially in Indonesia, right? Because the road is off-road. How is the road in Maltese?
and way better. We have like asphalt that we can drive our
I know.
car. So good.
You know, when I went to even other Southeast Asian countries like Vietnam or Thailand, their asphalt is much smoother,
Even Malaysia.
much smoother.
And you don't have even
Yeah.
asphalt. You have like cement on the highway. Who has cement on the highway?
When I went to Japan, man, I look at their road, it's like
Clean.
smooth, clean, and nicely curved. You know, I look at it,
There's no like bubble or anything.
it's like, I can even sleep on it. It's like that nice. And it's no garbage. Anyways, yeah, keeping it on the ground and maintaining contact to the ground is actually the most important function of a suspension, because what good is 300 horsepower if you cannot put it to the ground, right? It just floats. Yeah, so suspension is actually a second order system. Have you taken control systems with Pak Boris?
Yes.
Yeah.
Yeah? You will be introduced with what is called a second order system. Basically, you have a mass on a spring and a damper. Okay? So the mass, the spring, man, it's been a while since I teach this course. Damping is usually the variables B. So you have M, X double dot, KX, BX dot. Okay? So this motion is governed by a second order system. And from a practical point of view, this guy is the hardest to control. I mean, the spring and the damping, you just put whatever you want on it, right? You want performance, you want this, you want that. Even they have adaptive valve to adjust the beat. The spring cannot adjust. But the mass, you are kind of limited. And this mass is called the unsprung mass. Unsprung meaning that this is your wheel. Above this is your car, right? So your car, your chassis, is supported by the spring. But how much this wheel, okay, I'm just going to draw it like this, okay? How much this wheel touch the ground depends on this dynamic. And the hardest to control is M. And it's not hard because it's an engineering challenge. It's a financial challenge. Because you need to make your wheel very lightweight. So the mass that is below the spring is what's most important. Because the tires, the wheels, the brakes, the disc brake, the hub, the bearing, they're all pretty heavy. So anything that goes up and down here, the more lightweight you make it, the better you're handling. And that's why people pay a lot for lightweight alloy wheels. Of course, my alloy wheel looks great, but it's not lightweight. Because the real racing wheel is not prioritized for aesthetics. The priority is the lightweight. And it's expensive. It's also expensive to repair. So that's all I'm going to say about that for now. There are other subsystems. Let's go through them. Okay, this is part of the engine, by the way, right? So you have cooling, you have the intake box, yeah, you have the exhaust, and then you have the fuel tank. The thing with performance modifications, people often tackle the exhaust, right? But if you don't have anything, any pressure to relieve, then the exhaust really makes very little difference. It's like 5 horsepower. It's nothing. It's more psychological than real. Okay, if you buy an exhaust performance exhaust. But usually your exhaust and your intake will yield much more effect if you have turbo on it. So you have to have the mass, a lot of air to process in order for your performance upgrades to make sense. So yeah, we talked about that. Everything is unibody now. Yeah, so the exhaust. What is the job of the exhaust?
For what is it? Pollution perspective is
Okay.
to reduce carbon.
The catalytic converter removes pollutants like NO2, NO3, SO2, SO3.
Noise limitation.
Noise, the muffler.
Remove back pressure.
Remove back pressure. And again, the trade-off, right? Which one do you want? Performance or silence? But one area where people often underestimate in removing back pressure is the header. So this is the engine, this is the exhaust valve, intake valve, piston, connecting rod, crankshaft. So the air have to escape. And here is your header. And then goes to the exhaust. A lot of people thought that bigger headers are better. It's not. And why is that?
It's usually to have bigger header, but the exhaust is like pulsating. So the more corner you have, the more the pulse. It's just like traffic. If it's straight road, it's like easier to go. The straighter it is,
Like the
the
flow,
easier you go, the
is-
faster you go.
Okay.
But when you have that corner, it tends to break like this, break like this, break like this.
Okay.
So that's why.
But what about the diameter? Outside of the bends. We're not talking about the bends, but the diameter. Is bigger always better? The answer is no. Because of the scavenging effect. When you want to get the combustion products out, there are fresh air coming in. Around the same time, there is some overlap actually. So when the piston goes up to get the air out, the combustion product out, the intake valve actually opens a little. The purpose is for the fresh air to actually help push out. So actually pushing out the combustion gases is a big challenge. And that is a big factor in producing power, reducing pollutants, and fuel efficiency. So this is one of the things that engineers have trouble really improving your engine efficiency. Now, one way to help this process is actually the scavenging effect. So as the air goes out here from the previous, like you said, pulsating, right? From the previous pulse, that actually helps pull the combustion product out. Now, when you wash your car with a hose, let's say your hose diameter is this way, what happens when you put your thumb on it?
You have more pressure.
It's not more pressure, it's more velocity.
Yeah.
Okay, the pressure is the same because pressure comes from your source, right?
Source.
But when you put your thumb on it, you actually reduce the pressure, but you increase velocity.
Oh, yeah.
Bernoulli's effect, right? So when you have a pipe with water flow, and then you choke it,
The water will be faster.
you actually gain more velocity, but less pressure, right? Bernoulli's equation. Well, I ignore density because the density does not change. But pressure drops, velocity increases. And that's what happens when you do that in order for the water to go farther, right? So actually, if you want better scavenging, you actually make the header smaller. But you're introducing a little bit of a resistance. So again, this becomes a very difficult design decision, right? You make it smaller, you make it bigger. But bigger headers will be better for the high RPM range. And smaller headers will actually improve your low RPM torque because of the scavenging effect. That actually helps you. Now the dynamics is a bit different when you put a turbo in this. But without the turbo, for naturally aspirated engines, bigger headers help your high end. Smaller headers actually help your low end. So it's always a debate which one will be better, right? There is an oxygen sensor here. It measures, based on the combustion product, it gives feedback to the ECU, how much fuel you put in. These are the fuel lines. You get the fuel tank, get the filters in it, another filter along the way, fuel rail, injectors. The fuel is actually always circulating, by the way. It's not like you're pumping into a dead hole. You're not pumping into a jalan buntu, a dead end, right? You're not pumping into a dead end into the injector. The fuel rail actually have a return line and comes back to the fuel tank, always. So the pump actually always circulates, but it always maintains pressure on the fuel rail. And then you got the fuel injectors. Cooling system, what are some sensors on this? Temperature, obviously, the coolant temperature. You don't have pressure, you don't need to regulate the pressure, but there is a thermostat, right? What's the job of the thermostat in the cooling system? Why would you close it? Is it cold in your country? Just like here. So in colder weather, you will actually want the engine to heat up faster, right? Because it's more efficient to operate at the operating temperature. So there is a thermostat, and many cars also have electric thermostat now. So like European cars, they have electric water pumps, no longer mechanical. I hate it. It fails all the time. And they use plastic housing. Why? But
I used to work on the portion and on the end. So just to do like spark plugs and all this kind of regular maintenance, you need to remove the whole rear end, the exhaust.
man, It's Europeans.
You
That's
know
why
that-
I love Japanese cars.
The starter is in the transmission housing.
What?
Yeah, the starter
Inside?
is inside the transmission housing. So imagine you need to remove which
Oh,
this-
stupid engineer does that.
Oh yeah, it was so.
But yeah, the electric water pump and the thermostat, electric thermostat also fails a lot.
Actually, you need to change it every 75,000 kilometers. Yes.
The Japanese water pumps, they run forever.
Yeah.
They run forever.
True.
CV joints, constant velocity, CV. They actually compose of two universal joints, but it's in the same shape of a lobe. Well, we'll talk about it when we get there. Okay, so transmission, automatic, manual, very little manual nowadays. Too bad.
More CVT.
Hmm?
More CVT.
More CVT too. The automatics are mainly planetary. Running out of time. Yeah, a lot of the automatics are planetary, double planetary, and then you have two clutches to control, or three. This shown is the manual transmission. You got the flywheel. Anybody knows what a flywheel is and why we have it?
It transfers the energy from the engine to the transmission.
Okay,
Sticks to the
that's the clutch to be more accurate, right? The clutch actually transfers that, or torque converter in the case of automatics. But the flywheel itself is not the clutch.
the starter latches into it to start the engine.
Uh,
Oh, balancing.
outside automobiles, outside automotive, what is a flywheel and where do you see them? Do you know? Are you familiar with die punching machines? Like if you want to make stamp parts, like, well, that's die cast. Yeah, when you want to stamp these, the machine usually go up and down very fast, right? And then you put one sheet after another and then boom, 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 right? Now, this thing is driven by electric motors, but the forces of hitting the workpiece is often so big it will slow down your machine. So what do? They put a huge wheel on it, intentionally heavy. It's called flywheel. So a flywheel is actually a really big mass on this moving system, intentionally heavy to maintain constant speed. So you know how your engine keep exploding? Without a flywheel, the torque actually
Going up.
is fluctuating a lot because you're experiencing combustion, right? But with the flywheel, it actually dampens down that fluctuation. So it makes it constant torque. So the rotation is more stable with all these dynamics going on. Not the engine vibration, but the power. The power going out is more stable. And that's the purpose of a flywheel. You actually make it, it's a bit heavy, and they usually put the masses on the outside. So if you look at a flywheel, they often do this with a thick rim. So this is the huge mass. Not on the car, but on the machines, on the factory machines. So flywheels, clutch, main shaft, intermediate shaft, output shaft, differential. We'll talk more about that later. We need much more time for that. Differential in the back for rear-wheel drive. Also convert the direction. You know what type of gear they use? There's a bevel, bevel gear, right? We'll talk more about that. All-wheel drive have this transfer case. Oftentimes though, the shaft just goes out from the transmission housings. I don't see that a lot. Yeah, throttle, no throttle cable these days. It's all electronic. So sensor here, motor there. no cables. Brakes, clutches, talk about wheels a bit. Stabilizer bar, what's the purpose?
So if you're going this way, to pull the suspension
Yeah.
down, this way.
So it basically links the left and right. So without this, they move independently, which is good, but it results in a lot of roll, a lot of sway. And so it makes it so that when you compress this, it also, make it stiffer. So this becomes an additional stiffener. So when you move this, you also compress the other one. So you reduce the roll that way. Bigger bars, bigger diameter result in bigger effect of this. But if you make it too big, it becomes uncomfortable. Because this thing is only functioning if you are actually cornering. But what happens when you are going just straight and then you feel one bump on the left? Because of this guy, you also bump the right side. Get it? So this is also, if you make this too stiff, your right becomes harsh. Because when you're going a certain bump only on the left, because of this bar, it also bumps the right side. But if it's thin, then it's not much effect. Subframe. During assembly, oftentimes the engine is assembled on the subframe first, and then the whole thing just goes up from under. Because I worked at Honda previously, and that's what they do in many front-wheel drive. They assemble everything on the subframe, and then everything goes up with 4 big bolts. So that's why we can drop it if we need to drop the engine. Okay, McPherson style, cheap, a bit flexible here. So handling performance not that good, but hey, my wife will know because this is cheap. A better one would have an upper arm, so you have a double wishbone, and then the strut goes down rather than this one. We're asking what the essence of a McPherson strut system is that we are expecting the shock absorber to be the upper arm at the same time. So that's why with this design you see a bigger shaft here, bigger body, because we're expecting this guy to also hold the hub this way. The rear ones are usually less complex, just a torsion beam. The downside of this, make a guess. What's the downside of this versus the independent one?
One side lifts up, the other side.
Yeah, so it's just harsher, less comfort. I think most sedans are not torsion beam though. I mean, they will have independent, but the shape of this is still different geometry than the front. So it's still less comfortable. Okay, steering racks. Control systems. What kind of control systems for electric power steering? Used to be all hydraulics. Motor,
Angle sensor,
angle sensor,
pressure sensor.
No hydraulics for electric power steering. What does it need to sense? What does the power steering, what does the EPS control unit needs input of? Angle? How does it know when to actuate the motor? Because, see, if you don't touch the steering wheel, it's not going to move it, right? It's not supposed to. It's only when you encounter some effort. How does effort measure? Not pressure. The shaft will undergo some twisting, right? So there is a torque sensor. It senses basically they put a strain gauge on the steering shaft, and when you shift it, the strain gauge senses displacement. Very tiny, but that's how they sense the torque. So the more effort you put, the more current they put to the motor to assist you. But they assist based on how much torque. So that's why you don't feel this. This is happening in real fast, real time. And so when you have some effort, the motor immediately helps you. And so what you feel is nothing. But you got the motor. This is where the sensor is. So it commands the motor to move, not based on the angle, but based on the effort. Braking system, the emergency brake, the philosophy is always that the emergency brake has to operate with a different system. So if this is hydraulic, the handbrake is mechanical. It's using a cable. So you need to have redundancy. So if the hydraulic fails, this one is not affected. Or nowadays, they put electric power, electric brake, right? Either way, one is hydraulic, one is electric, that's fine. Two independent systems. In brakes, you have ABS,